Alright, so I'm going to finish my examples for section 1.6 for you guys so that while I'm gone you can see what's going on. So again, this example says symbolically find delta in terms of epsilon. So we're going to start with our same basic things that we had. We do x minus a less than delta, and we have f of x minus the limit less than epsilon. So we're going to start all of our problems with this same basic definition. So again, just like yesterday, L is equal to -1, A is equal to 1, and my function is the stuff after the limit. In order to do this, I'm going to have x minus 1, and the absolute value of that is less than delta. So I'm going to plug in my other stuff. So my function could be written as -4x plus 3, and I think it'll be a little easier to write that. So -4x plus 3, and then I've got to add or subtract my limit from that. So if I subtract a -1, I'm adding 1. And there's my epsilon. Let's go ahead and simplify this a little bit. If I add 1 and 3, I get -4x plus 4, and hopefully you can see if I factor out a -4, it would leave me with x minus 1. However, I'm doing the absolute value of that, so I can just write a 4 out here. And now you can see if I divide both sides by 4, I essentially have x minus 1 left over. So that tells me my epsilon and my delta relationship, and delta equals epsilon over 4 for this example. Now, again, as we look at these, we got to know how to start. So again, we're always going to start with our basic definition. So in this case, my a is equal to 1, so I'm going to have x minus 1, and that's going to be less than my delta. I'm going to have my function, which is x squared plus x minus 2 all over x minus 1, and I'm going to have to subtract my limit. Okay? Now this one's a little different because we've got a -3 after this function. So in order to get rid of this and to put these things together, I am going to have a common denominator. So that means x squared plus x minus 2 over x minus 1. And in order to have a common denominator, I'm going to have to multiply top and bottom. So you got to remember that 3 is over 1. I got to multiply both by x minus 1 in order to simplify that down. Once I do that, I've got x squared plus x minus 2. And then that's going to be minus 3x. So minus 3x. And then I'm going to take minus 3 times -1 and get plus 3. And since I'm combining my fractions, I've got x minus 1 on the bottom. So I skipped a few steps here just to try to save some space. So I've got x squared. I don't have anything else like it, so I'm going to put x squared on top. I got a plus x and a minus 3x that give me -2x. And I've got a -2 plus a 3 that give me plus 1. Now, if you look at this closely, you should hopefully know the top factors and do x minus 1 squared. And that's over x minus 1. And my last step with that I'm going to draw an arrow to show you my last step, would be to take one of those x squareds away, one of these top parts squared, x minus 1 squared away, because I'm dividing by x minus 1. So that leaves me x minus 1 is less than epsilon. So I'll circle that. We'll bring it over here and talk about what it means. So if I have this situation, all right, that means that delta has to be less than epsilon, and that would be my relationship. All right, so as long as I have a delta less than epsilon, I can show that this limit equals 3. Now, if limits involve infinity, things are a little different, but it's not too bad. So for a function f defined on some open interval containing a, but not necessarily at a itself, we can say that the limit as x approaches to a goes to infinity if we have a number that we can find m that's bigger than 0. All right, we can find another number delta that's greater than 0, so that we have our interval just like we had before. So somewhere between 0 and delta we have this x minus a, and we'll guarantee that the function is bigger than this number m. So I can show you what that looks like graphically. Alright, so pretty much what this looks like graphically is that if I have my function, and my function shooting up towards my positive infinity, let's say I've got another piece of it down here. Alright, we got our a value here that it's shooting up towards but never quite reaches infinity. Alright, I guess I should redraw my function to actually show like this. Pretty much what we're saying, that if we can get to this number m, we can pretty much show that my function is going to be bigger than this really big number, and that we're going towards infinity. Alright, and we can do the same kind of idea. If you look in the book, and if you look at the section, you can see like the diagrams, kind of like I tried to sketch out there. So look at those and see, make sure that makes sense. Alright, for a function f, again, we can do the same thing with the negative infinity. Alright, except for this, we have n less than 0. So that means I have a really big negative number. So again, I think once you see how these things work, this part will be a little easier than what it looks like right now. Alright, and if you need to pause this and write some of these things down, that's fine. Now, if we have a function that's and x is approaching infinity, we can find a number epsilon greater than 0, and then this m is greater than 0, such that x greater than m guarantees that my function minus my limit is less than epsilon. So this kind of combines the other piece where we're going, our function going out towards a horizontal asymptote, and we need a number m that x is bigger than. Same thing holds true when you go towards negative infinity on your x. So this looks a lot the same, except it goes the other way on the graph. Alright, so this graph will go out here towards negative infinity. You got some value out here that we're going to try to get x bigger than, because if we can show that x is bigger than or less than n, then we can show that this limit definition will work. So what we're going to do with those kinds of problems is we're going to find a delta value corresponding to an m value or an n value, and figure out what delta value we need to make this true. So we're pretty much going to use this, x minus 1 less than delta. And we're going to find the delta value that goes with this m or n value of 100. In this case, I'm approaching a positive number, so I'm actually going to use this, the m equal to 100. So that just means I need to make my function, my 2x minus 1, bigger than 100. Alright? Now, to solve this easily, you got to remember a couple little things about equality. Alright, and this is 100 over 1. So if I take two sets of fractions and just flip them over, I haven't changed what I have as far as the equation goes. Alright, now I can take and multiply both sides by 2. And then when I multiply it by 2, I see my left hand side is x minus 1, and that's greater than 2 over 100, and 2 over 100 is also equal to 0.02, and that means when we look at this, it pretty much matches this definition, x minus 1 less than or equal to delta, so delta has to be 0.02. Alright, this limit I'm going towards infinity, and I need to find an m value or an n value that goes with an epsilon of 0.1. So since I'm going towards positive infinity, I don't need the n value, I need the m value. So in order to do this, I'm going to have to use the function minus the limit, and set that less than 0.1 because that's my epsilon. So again, I'm just using my second piece of my definition. My function minus my limit has to be less than this epsilon value. Okay, so we're going to solve this. In order to solve this, we got to get a common denominator. In order to have a common denominator, I have to have x squared plus x plus 1 . Now, we got to keep going, so we can do minus x squared from the x squared. We got a minus x. Alright, so I'm just going to take these away from the things that I can do from. I got negative 2, and I can minus 1 from that and get minus 3. And then, since I've got this less than 0.1, I can rewrite that as a fraction. Now, one of the things we can do, since this has the absolute value, let me go ahead and give myself some more room to write. Alright. Is I can make this top into, I can pretty much get rid of the negative 1 and do x plus 3, so I can factor out a negative 1 from that. And essentially what I can solve to figure out my m value I need to be bigger than is this. Now, I can cross multiply this, so I do 10 times x plus 3 and get 10x plus 30 equals x squared plus x plus 1. And then I got to solve this quadratic by setting this left side equal to 0. So that gives me x squared. I got x minus 10x, so that's minus 9x. And then 1 minus 30 is minus 29. Alright, I'm not going to show all the work to find the zeros here, but if you punch these into the quadratic formula, you will see that you get x equals negative 2.5, or you'd get 11.5. And if you notice, we're going towards positive infinity, so I need a number m. My number m would have to be bigger than that, so let's go ahead and just say it's 12 to have an even number, and that would guarantee that we are above where we're going. Alright, if you get past 12 on this function, it guarantees that that limit is equal to 1. Alright, so for number 7 here, again, got a limit going to infinity, and we got 2 over x cubed, and we got our limit equals 0, so we're going to use the function minus the limit less than epsilon. Alright, and that pretty much gives us 2 over x cubed less than epsilon. Alright, so we're pretty much going to be solving this. So 2 over x cubed. If we can set that equal to each other and solve this for x, we can find the m value that we have to be bigger than. So in order to solve this, again, it's kind of like cross multiplying. You can switch the epsilon and the x around and get 2 over epsilon equals x cubed, and then take the cube root of both sides and see that you get the cube root of 2 over epsilon, and that will be our m value. So in this case, as long as m is over the cube root of 2 over epsilon, this limit will be correct. And for number 8, we got our negative infinity, so we need to figure out a delta in terms of m, or n. Since we're going to a negative infinity, we get the n value. So for this, we're going to have x minus a, so x plus 3 in this case, has to be less than delta. That pretty much means that negative 2 over x plus 3 to the 4th has to be less than my n value that I'm looking for. Okay, so I can do a little switcheroo here. And when I do that, I can solve both sides by taking the 4th root. I get x plus 3 over here. I get the 4th root of negative 2 over n. And if you've been keeping track of what we've been doing, these two things are the same, so that means that delta has to equal the 4th root of negative 2 over whatever the n value is. And that was all I have. Those last few things will help you get the last few examples finished.